Welcome to a crash course in Deep Deterministic Policy Gradients, or DDPG for short. In this lecture, we're going to briefly cover the fundamental concepts and some notes on the implementation so that the stuff we do in the coding portion isn't such a mystery. So why do we even need DDPG in the first place? Well, DDPG exists to answer the question of how do we apply reinforcement learning to continuous action spaces. This is particularly important in something like, say, robotics, where we are applying continuous voltages to electronic motors that cause the robot to move in three-dimensional space. Now, you may think, well, why can't we just use something awesome like deep Q-learning? And that's not such a terrible idea. However, the problem is it doesn't work. In particular, Q-learning can't handle continuous action spaces. If you've coded up a Q-learning network, a deep Q-learning network that is, you know that it outputs discrete numbers as actions. And of course, that doesn't cut it when you're dealing with continuous action spaces. Now, you might think, why can't we just discretize our action space? And that's not such a bad idea, but the problem is it doesn't work. And the basic idea here is you have some finite interval for your action space, and then you just divide it up into a number of discrete chunks, and then every time you want to output the action in that chunk, you just use that discrete integer. The problem with this is that these robots tend to have many degrees of freedom, meaning they can move in many different directions in space, right? They can rotate around axes, multiple axes in general. They can move up, down, left, and right. They can rotate. And so your number of discrete actions approaches the thousands very, very quickly. And so Q-learning, while it does handle discrete action spaces, doesn't handle large numbers of discrete actions particularly well. However, that doesn't mean that the innovations from Q-learning can't be applied to actor-critic methods, and in fact they can, and that was the motivation behind the work done in the DDPG paper. In particular, we're going to make use of a replay memory, where instead of just learning from the most recent state transition that the agent has experienced, it's going to keep track of the sum total of its experiences and then randomly sample that memory at each time step to get some batch of memories to update the weights of its deep neural networks. The other innovation is the use of target networks. So in Q-learning, we have to do two different things. We have to use a network to determine the action to take, and then we have to use a network to determine the value of that action, and that value is used to update the weights of the deep neural network. Now, if you're using the same network to do both things, the problem is you end up chasing your tail. You end up chasing a rapidly moving target because at each time step those weights are getting updated, and so the evaluation of similar actions the evaluation of similar states changes rapidly over the course of the simulation, causing the learning to be unstable. The solution to this is to keep two networks, one of which you use, the online network is called, to choose actions at each time step, and then another network called a target network to evaluate the values of those actions when performing the update for your deep neural network. Now, in this case, you will be doing a hard update of your target network. So every, let's say, 1,000 steps, it's a hyperparameter of your agent, but a typical value would be 1,000 steps. You would take the values for the network parameters from the online network and directly copy those over to the target network. It's what's called a hard update. The authors of the DDPG paper took inspiration from this, but instead of doing a direct hard update, they used something called a soft copy of the target networks. All this means is that we're going to be doing some multiplicative constant for our update, and we're going to be using a new hyperparameter called tau, and it's going to be a very small number of order 0.001. It's also worth noting that we're going to have more than one target network here, and the reason we need more than one target network is because DDPG is a type of actor-critic method. And so you have two distinct networks, one for the actor and one for the critic. And in fact, in this implementation, we're going to have 4 different networks, one actor, one critic, and then one target actor and one target critic. Now, for simple problems with discrete action spaces, you can get away with having a single network where the lower layers learn the features of the environment and the upper layer splits off into outputting the critic evaluation as well as the output for the actor network, but in this case we do in fact want two totally distinct networks, as well as two copies of those for the target networks. The basic idea is that our critic network is going to evaluate state and action pairs, and so we're going to be passing in states and actions, and it's going to say, hey, given that state, the action we took was pretty good, or maybe that action was pretty terrible, we should probably do better next time. And similarly, the actor is going to decide what to do based on the current state or whatever state we pass into it. Something worth noting is that this network is going to output action values. In other words, a continuous number that corresponds to the direct input for our OpenAI Gym environment, rather than outputting probabilities. So if you've been doing this for a while, you may know that the policy is actually a probability distribution. It is a function that tells us what is the probability of selecting any action from the action space given an input of a state or set of states. The deterministic part comes from the fact that DDPG outputs the action values themselves, and it's deterministic in the sense that if I pass in one state over and over again, I'm going to get the same action value out every single time. Now, this does have a bit of a problem. So the problem is that the agent has something called an explore-exploit dilemma, and this is present in all reinforcement learning problems. It's a fundamental concept in the field. The basic idea is that our agent is attempting to build out a model of the world. The agent wants to know how to maximize its total score over time, but it starts out knowing absolutely nothing about its world. It has to figure out how states transition from one into another and how its actions affect those states, and in particular how its actions give it rewards. So it starts out knowing none of this and has to build out that model over time. The problem is the agent can never be quite sure that its model is accurate. No matter how long it spends playing the game, interacting with the environment, it isn't 100% certain that the action it thinks is best is actually the best. Perhaps there's some other strategy, some other action out there that is significantly better. And the degree to which the agent takes off-optimal actions is called the explore-exploit dilemma. So of course, taking an off-optimal action is called exploration, and taking the optimal action is called exploitation, because you're just exploiting the best known action. And this is a dilemma that is present in all reinforcement learning problems, and the solution here is to take the output of our actor network and apply some extra noise to it. Now in our implementation, we're going to be using simple Gaussian noise because it's sufficient for the problem at hand. However, in the original paper, the authors use something called Ornstein-Uhlenbeck noise. It's a model of Gaussian processes in physical systems. It's overly complex and it's not needed, so we're not going to implement it. Although in the course, I do show you how to implement it exactly, but for YouTube, it's not really necessary. And in fact, when other authors implement DDPG, they just throw that right out the window because it's pretty dumb. Next is the update rule for our actor network, and it is somewhat complex. So I'm going to show you the equation, and then I'm going to walk you through it. So this is the update for the actor network, and don't panic, this is a little bit easier than it looks at first glance. So from left to right, we have the nabla operator, that is the gradient, and the subscript there, theta super mu, means that we want to take the gradient of the cost function j with respect to the network parameters of our actor network, where the actor is denoted by mu and its parameters are denoted by theta super mu. So theta super q means the parameters for the critic network, where the critic is denoted by q. And that's just given by an expectation value or an average of the gradient of the critic network, where we're going to input some states and actions, where the actions are chosen according to the current policy. Okay, so in practice, what this means is what we're going to do is randomly sample states from the agent's memory. Now the memory keeps track of everything we want. It keeps track of the states the agent saw, the actions it took, and the new states that resulted from those actions, as well as the reward the agent received at that time step, and the terminal flag to determine whether or not the episode ended on the new time step. So the memory keeps track of all of that, but here we just want to sample the states the agent saw, okay? And then we're going to use the actor network to determine what actions it thinks it should take based on those states. Now these actions will probably be different from the actions we have stored in memory, and that's okay. This is off policy, meaning we're using a separate policy to gather data and use that data to update a different policy, the current policy. So it's okay that these actions don't match. Don't worry about that. It all works out in the end. Then the next thing you want to do is plug those actions from the actor into the critic network along with the states we sampled from the memory and get the value for the critic network, what it thinks that state action pair is worth. And then we're going to use the gradient tape from Tensorflow 2 to take the gradient of the actor network, the critic network with respect to the parameters from the actor network. And we can do that because they're coupled through the selection of the actions based on the actor network. Okay, so it's a little bit complex. It's much easier in code. Just in code, you sample the states, then you get the actions based on the critic network, and then plug those states and actions into the critic network, and then you just have the loss proportional to that. It's actually much simpler in code than it is on paper, but that's the basic idea. So then the next question is, how do we implement our critic network? Well, fortunately, it's a little bit more straightforward, and it's more reminiscent of deep Q-learning. So we have this relatively simple loss function that is the mean squared error between this target value y sub I and this Q for the current state and action. So what we're going to do here is randomly sample states, new states, actions, and rewards, and then we want to use the target actor network to determine the actions for the new states. Then plug those actions into the target critic network to get your y and multiply it by the discount factor gamma and add in the reward from that time step, which you sampled from the memory. And then that is a target, the value we want to shift the estimates for our critic towards. And then we want to plug the states and actions into the critic network. In other words, the actions the agent actually took that we sampled from our memory. This is in contrast to the update for the actor network. And take that difference with the target. And then we're going to input it into the mean squared error loss function for Tensorflow 2. So in code, this is going to be relatively straightforward as well. We're going to have a sample function to get states, new states, actions, and rewards. We're going to plug in the new states into the target actor network, get some output. We're going to plug that output into the target critic to get our target y, and note it is s sub I plus 1, so it is the new states that we get from our memory buffer. And then we're going to plug the current states and actions from our memory into the critic and take the difference with the target. So it only looks kind of scary on paper. When you see it written in code, it'll make much more sense. So the other piece of the puzzle is how we're going to handle the updates of our target networks. So at the very beginning of the program, we are going to initialize our actor and critic networks with some parameters. Of course, they're going to be random. And then we're going to directly copy those parameters over to our target actor and target critic networks. That'll be the only time in the simulation that we do an exact hard copy. Every other time step, we're going to use the soft update rule. So here you have the two parameters, theta super q prime, so the weights of the target critic network, and theta super mu prime, which is the weights of the target actor network. You're going to update those with tau multiplied by the respective value of the online network, the critic or the actor, and add in 1 minus tau times the current value of your target actor or target critic network. And so this will be a very slowly changing function because it's going to be some small number tau multiplied by some parameters plus 1 minus tau, which is approximately 1 multiplied by the current value. So it's going to be approximately equal to its last time step, just plus minus a little bit. So it's relatively straightforward. We'll see it in code. It's not all that bad. So then the next question is, what data structures are we going to need for all of this? So we're going to use a class to encapsulate our replay buffer, and that will use NumPy arrays. There are a myriad of different ways to handle the replay buffer. I like the NumPy arrays because it's easy to enumerate, it's easy to know what is being stored where. and it makes for an easier YouTube video because it's easier for people to see what's going on. If you have a different way of doing it, by all means use that. It's not something for which there is only one right answer. We will need one class each for the actor network and critic network, and those will be handled using the TensorFlow 2 framework. These will have the functionality to perform a forward pass as well as the usual initializer function. We will also need an agent class to tie everything together. The agent will have a functionality for the memory, right? It will have a memory buffer to store memories. It will have the actor network, critic network, target actor, target critic network. It will also have a function for choosing actions based on the current state of the environment, and that will involve passing a state through the actor network, getting the output and adding in some Gaussian noise. It will also have functionality to learn from the memories it has sampled, and it will also have functionality for checkpointing models because this can take quite a while to train for complex environments. We're going to use a simple environment, but if you want to go ahead and try something more complex, the checkpointing functionality will come in handy. Finally, we will need a main loop to train our network and to evaluate its performance. All right, that has been a very brief introduction. Let's go ahead and get into the coding portion of our video. All right, now that the lecture is out of the way, it is time for a shameless plug. In my courses, I show you how to go from paper to code rather than relying on someone else to break down the material in the paper for you. It's the best way to gain independence and to level up your skill as a machine learning engineer. Provided through Udemy, they are on sale right now. Check the link in the description below. Let's go ahead and start with our buffer. So the point of our buffer is to store the states, actions, rewards, new states, and terminal flags that the agent encounters in its adventures. And we're going to use, as I stated in the lecture, NumPy for this. It's going to be relatively straightforward. The reason I use NumPy is because it makes it much more clear what everything is. It's just a little bit simpler and cleaner from an implementation perspective, although it is by no means the only way to do things. So the first thing we'll need is a max size. The memory is bounded, and input shape from our environment, and a number of actions for our action space. Now in this case, since it is a continuous action space, number of actions is a bit of a misnomer. What it really means is the number of components to the action. The purpose of the mem size is that the memory cannot be unbounded, and our memory will have the property that as we exceed the memory size, we will overwrite our earliest memories with new ones. So for that, we will need a memory counter. It starts out as 0, and then we can go ahead and start with our actual memories. First, we have a memory size, a state memory, and that will be in shape memory size by input shape. We have the new state memory, which is in the same dimensions. We need an action memory, and that will be in shape mem size by n actions. And one thing I want to make clear, there was a question on the Discord server. By the way, also check the link in the description for the Discord server. We have many really bright people in there talking about a lot of complex stuff. It's a great little community. I would encourage you to join. But the question popped up whether or not I'm writing this stuff on the fly, and I am not. I don't know if that was clear. You can often see me looking off to the side here. That's because it's not a second monitor. It's just a really large monitor where I have a second window open with the already completed code. And if you've seen my tutorials before, you know that I make a lot of typos, and so the probability of making a logical error where I have state instead of new state, for instance, is incredibly high, and that when you are making YouTube videos is enormously painful to try to do everything from memory and then swap states with new states and then not have it work and then have to go back and re-record. So it's just easier to have the already written code, and I'm kind of reading off of it as I go along, and occasionally I'll make modifications. So all of the code is mine, but it is not written on the fly. I just want to make that clear. Next, we'll need a reward memory, and that is just shape mem size, and that is just going to be an array of floating point numbers. And we will need a terminal memory, and that will be n-type Boolean. I use Boolean because in PyTorch we can use masking of tensors. I don't think it works in Tensorflow, so I'll have to do something slightly different in our learning function, but I will note that when we get there. We'll need a function to store a transition, where a transition is the state, action, reward, new state, and terminal flag. The first thing we want to do is determine what is the position of the first available memory, and that's given by the modulus of the current memory counter and the memory size. Once we have the index, we can go ahead and start saving our transitions. Yeah, see, I've already made a mistake here. Then we have action memory, and terminal memory. And we want to increment our memory counter by 1. Now, one thing I don't think I stated in the lecture, the purpose of this terminal memory is that the value of the terminal state is 0, because no future rewards follow from that terminal state. We have to reset the episode back to the initial state. So we have to have a way for accounting for that in our learning function, and we do that by using the terminal flags. Excuse me, by using the terminal flags as a multiplicative constant in our learning function. Next, we need a function to sample our buffer, and that will take a batch size as input. We want to know how much of our memory we've filled up, because we have a memory and it starts out as entirely zeros, and until we fill up that memory, some portion of it will be nothing but zeros. It doesn't do us any good to learn from a bunch of zeros, so we have to know how much of the memory we've actually filled up. And this is given by the minimum of the memory counter or the mem size. Then we can take a batch of numbers, random choice, max mem, batch size, and I think I want to pass the replace equals false flag in there. I don't have that in my cheat sheet, but the point of passing in replace equals false is that once a memory is sampled from that range, it will not be sampled again. That prevents you from double sampling memories. If you're dealing with a really large memory buffer, the probability of sampling two identical memories is astronomically small, but up until that point, it's non-negligible, so we should be careful. Then we want to go ahead and dereference our NumPy arrays. And we will return those at the end. That is a typo. All right, that wraps up our replay buffer class. Now we're going to go ahead and handle the network classes. All right, so our imports are relatively light. We will need OS for file path joining operations for model checkpointing. We will need the base TensorFlow package. We will need Keras, and we will need layers. Now, we're going to be dealing with a very simple environment, so we just need a dense layer. We don't need any convolutional layers. So we will start with a critic network, and that derives from the Keras model class. That will take a number of actions, number of fully connected DIMMs, a name, and a checkpoint directory. Now, very important, you must do a makedir temp and makedir temp/DDPG before we run this, so that you can actually save your models. Otherwise, you'll get an error. Let's go ahead and call our superconstructor. and then start saving our variables. We have to call our model name due to the TensorFlow package keeping name as a reserved variable. You can't just say self.name. It'll give you an error. Not a huge deal, just something to be aware of. Then we'll have our checkpoint file. And Keras models get saved with a .h5 extension. And I throw in the model name because we're going to want to distinguish between the target and regular networks. And I add an underscore DDPG because if you do development in a single directory, then you don't want to overwrite models from, say, TD3 with DDPG models, vice versa. It's just a way of keeping all of your models distinct and very secure. Next, we need to define our network. So our first fully connected layer will output self.fc1 dims with a ReLU activation. Then we'll have fc2 dims ReLU, and our final output layer is single valued with no activation. A couple of things to note here is that in the original paper, the authors use batch normalization. Turns out that isn't necessary. In the course, I show you how to implement that, but it's just an overly complex implementation. It doesn't actually add much to it. They also do a number of kind of tweaks with the initialization of the layers. We're not going to do that here. I show you in the course, but it's not really necessary. Next, we need our call function. This is the forward propagation operation, and this is the critic, so it takes a state and action as input. So we want to pass the concatenated state and action through our first fully connected layer, and we'll concatenate it along the first axis. The 0th axis is the batch, and then we will pass the output of that through the second fully connected layer, and we will go ahead and get our Q value out and return it. That is it for the critic network. Very, very straightforward. Next, we have our actor network, and that is pretty similar. Equals 512 and actions. I'll just default to 2. Name equals actor, and checkpoint dir. And you know what? Now that I'm looking at this, we don't need the number of actions here, do we? Because we don't use it. Let's get rid of that. Yeah, I'm looking at my cheat sheet as well. These are some of the modifications I make as I go along. Sometimes I'll have stuff that doesn't always make 100% sense, and then when I do the YouTube video, I go ahead and rectify it. So we'll go ahead and call our super constructor and save our values. This time we will need the number of actions because the critic network does, the actor network does need to know how many actions it has. And we will need our checkpoint dir. And then our model is going to be pretty similar to the critic network. It's going to be a number of fully connected layers with a ReLU activation. Now, We don't want a null activation here, no activation, or linear activation, if you will. We do want an actual function here. And what we want is a function that is bounded between plus and minus 1. And the reason is that most of our environments have an action boundary of plus or minus 1. However, if the action boundary is larger than plus or minus 1, it's easy to get the action within that range by multiplying a function which is bounded by plus or minus 1 by the upper bound of the environment. So if your environment has a bound of plus or minus 2, then you would just multiply the tan hyperbolic function, which is bound to plus or minus 1, by 2. Next, we have our call function. We'll go ahead and call it prob. It's a bit of a misnomer. These aren't really probabilities. And then we will get our mu, which is from the paper. It's our actual action. Now, if you had not plus or minus 1, can multiply here. You can multiply it there, or you can multiply it in the agent class when we do the choose action function. Either way is logically the same. I would probably do it in the agent class just for my own personal preferences, but either way, you want to multiply the output of the deep neural network by the bounds if those bounds are not plus or minus 1. All right, that is actually it for the network classes. Let's go ahead and code up the agent class and tie all of this together. Okay, our imports will be quite numerous. We will need NumPy, Tensorflow, we will need Keras, we will need our optimizers, which we use Atom for this project. We will need our replay buffer, and we will need our actor and critic network. Did I misspell that? Nope, that looks correct. So here's our agent class, and we have an initializer, and that will take input dims, a learning rate for the actor network alpha, a learning rate for the critic network beta. These are distinct, they're not the same, and in fact the critic network can get away with a slightly higher learning rate than the actor network, and that is because in general in policy gradient type methods the policy approximation is a little bit more sensitive to the perturbation in parameters. So if you wiggle around the parameters of your deep neural network, you can get big changes in the output of the actor network. And so it has to have a slightly smaller learning rate with respect to, say, like the critic network. We will need our environment for the max and min actions because, as I said in a lecture, we're going to be adding noise to the output of our deep neural network for some exploration, and we have to clip that into the max and min actions for our environment so we don't trigger an error when we try to pass that action into the OpenAI gym. We will need a gamma, and that is the discount factor for our update equation, number of actions, a max size for our replay buffer, defaulted to 1,000,000, a default value for our soft update of 0.005, that's from the paper, a default for FC1 and FC2. In the paper they actually use 400 and 300. I'm going to go ahead and do that now rather than in the main program. That makes life a little easier. A batch size for our memory sampling, and a noise for our exploration. So let's go ahead and save our parameters, gamma and tau. We can instantiate our memory. We can save our batch size. And our noise. And then we'll go ahead and get the maximum and minimum actions for our environment. Then we can instantiate our actual networks. So our actor, our critic, our target actor, and our target critic. That is it for our networks. Now we have to actually compile those. We will use our atom optimizer with learning rate defined by alpha. Similarly, for our critic network, we will give it a learning rate of beta. And then we have our target networks. That is a bit of a misnomer because we aren't going to be calling the we aren't going to be doing gradient descent for these networks. We're going to be doing the soft network update, but we have to compile the network, so we have to pass it a learning rate. It's just a feature of TensorFlow. Don't get confused if down in the learn function we don't actually call an update for the loss function for these target actor and target critics. Then we have to call our update network parameters function, and this is where we do the hard copy of the initial weights of our actor and critic network to the target actor and target critic network. And I'm passing in tau equals 1 to facilitate that hard copy. Let's go ahead and write that function now. And so we have to deal with the base case of the hard copy on the first call of the function and the soft copy on every other time we call the function. So if tau is none, in other words, if we don't supply a value for tau, then just use the default defined in the constructor. And so you notice here, the first time I call it, tau is 1, so tau is not none. So we're going to be using a value of 1 for tau instead of the 0.005. So we'll say weights is an empty list, and our targets will be target actor weights, or I weight. We're going to iterate over the actor weights and append the weight for the actor multiplied by tau plus targets sub I, now which is the weight from the target actor times 1 minus tau. And then after we go through every iteration of the loop, we're going to set our weights for the target actor to that list of weights. So in the first iteration, tau starts out as 1, and so you have weight times tau, which is 1, so just the actor weight plus the target actor weight multiplied by 1 minus tau, which is 1 minus 1, or 0. So on the first iteration, we get a hard copy. And then we do the same thing for the critic network. And that is all we need to do for our soft update rule. So now we'll go ahead and write an interface function for our agent's memory. They'll take a state, action, reward, new state, and terminal flag as input. And then we'll just call the store transition function. And this is just good, clean coding hygiene. It's an interface function when you have interdependent classes. In theory, we shouldn't be able to call the agent.memory.store transition from anywhere else in the program except within its own member function. It's just basic object-oriented programming stuff. Now let's deal with model checkpointing. And we'll say self.actor save waits actor checkpoint file, and likewise for our other networks. That should be a dot, not an underscore. I think I've done that before, that specific mistake. Of course, I have an extra space here. And the load models function is just the inverse operation. We say, what is it, self.actor.load waits .checkpoint file. Critic checkpoint file, yep. Okay, that is it for our basic bookkeeping type functions. Now we can get into the functionality for choosing an action. And that will take the observation of the current state of our environment as input, as well as a flag I call evaluate. This has to do with training versus testing our agent. Remember that we use the addition of noise for the exploration part of the explore exploit dilemma. If you're just testing the agent to see how well it learned, you don't necessarily want to add that noise. You can just do the purely deterministic output of your actor network, and I facilitate that with a Boolean flag here. First thing you want to do is convert our state to a tensor, and we have to add an extra dimension to our observation to give it a batch dimension. It's just what the deep neural networks expect as input. They expect a batch dimension, and I specify a float32 data type to be pedantic, and then we pass the state through the actor network to get the actions out. If we are not evaluating, in other words if we are training, then we want to get some random normal noise in the shape of self.n actions with a mean of 0.0 and a standard deviation of whatever our noise parameter is. Now, it's entirely possible that the output of our deep neural network was 1 or 0.999, and then when you add in the noise, you're adding in something like, let's say, 0.1, and you end up with an action that is outside the bound of your environment, because perhaps it's bounded by plus or minus 1. And so you want to go ahead and clip that to make sure you don't pass an illegal action to your environment. So we'll say actions equals tf clip by value. That's the function we want. Actions, and that is between self min action and max action. And then we want to return the 0th element because it is a tensor and the value is the 0th element, which is a NumPy array. Then we want our learning function, and this is where the bulk of the functionality comes in. And right away we are faced with a dilemma. So what if it's the case that we haven't filled up at least batch size of our memories? So remember that the memory starts out as all zeros, and if you've only filled up, let's say, 10 memories, you don't really want to sample those 10 memories batch size number of times. So you can just go ahead and say, well, I'm not going to learn. I'm going to wait until I fill up my memory until at least batch size number of memories. Alternatively, you can play batch size number of steps with random actions and then call the learn function. That's another solution as well, and they're both valid. I just find this to be a little bit more straightforward. So then we have to go ahead and sample our memory. And then we can go ahead and convert these to tensors. New states. That is singular, not plural. And we don't have to convert the terminal flags to a tensor because we're not going to be doing tensor operations with it. We're going to be doing regular NumPy array type operations. So we're going to use a gradient tape for the calculation of our gradients. If you're not familiar with a gradient tape, the basic idea is we're going to go ahead and load up operations onto our computational graph for calculation of gradients. So when we call the choose_action function above, those operations aren't stored anywhere that is used for calculation of gradients. So it's effectively detached from the graph. So only things within this context manager are used for the calculation of our gradient. And so this is where we're going to stick the update rule from our lecture. So let's go ahead and start with the critic network, where we recall that we have to take the new states and pass it through a target actor network and then get the target critic's evaluation of the new states and those target actions. And then we can calculate the target, which is the reward, plus gamma multiplied by the critic value for the new states times 1 minus a terminal flag, and then take the mean squared error between the target value and the critic values for the states and actions the agent actually took. So let's go ahead and write that out. So target actions is given by our target actor what it thinks we should do for the new states. And the critic value for those new states is going to be given by the target critic evaluation of those new states and target actions and squeezed along the first dimension. We have to put in this squeeze because we have the batch dimension, and it doesn't actually learn if you pass in the batch dimension. And I feel like I am missing, there we go, a parenthesis. So we'll have a squeeze everywhere that we had to actually pass stuff through the network. So then the critic value, which is the value of the current states, the original states, and the actions the agent actually took during the course of the episode, is given by the squeezed output of the critic for the states and actions along the first dimension. Yeah, I guess that is right. Yep. And then we have our target, and that's reward plus gamma times this critic value underscore times 1 minus done. So this 1 minus done is 1 minus true or false. So when the episode is over, done is true. And so you have 1 minus 1 or 0. And so the target for the terminal new state is just the reward. Whereas for every other state, it is reward plus the discounted value of the resulting state, according to the target critic network. I'm sorry if you can hear the landscapers outside. It's Tuesday. They're doing the neighbor's yard. Hopefully the noise suppression filter takes care of that, but if not, I apologize. Next, we have a critic loss, and that's the mean squared error between our target and the critic value. outside of the context manager, we want to go ahead and calculate the gradients. So we'll say critic network gradient equals tape.gradient critic loss self-critic trainable variables. So it is the gradient of the critic loss with respect to those critics trainable variables. And then we want to apply our gradients. So our optimizer dot apply gradients, and that expects a zip as input. We want to zip up the critic network gradient and the critic trainable variables. And that is it for the critic loss. Now we have the actor loss. So we want to do essentially the same thing. We want our context manager, gradient tape as tape. Then we say new policy actions, actor states. So these are the actions according to the actor based on its current set of weights, not based on the weights it had at the time of whatever memory we stored in the agent's memory. So then we have our actor loss, and that is the negative of the critic output of the states and the new policy actions. It's negative because we're doing gradient ascent. In policy gradient methods, you typically want to take the you don't want to do a gradient descent because that would minimize the total score over time. You want to maximize total score over time, so you do gradient ascent. Gradient ascent is just a negative of gradient descent, so we stick a negative sign in here. And then our loss is just the reduced mean of that actor loss. And then we can go ahead and calculate our gradients and apply them. So the actor network gradient is tape.gradient of the actor loss with respect to the actor trainable variables. And this is how we're going to get that gradient of the critic loss with respect to the mu parameters, the theta super mu, is by taking this actor loss, which is proportional to the output of the critic network, and that is coupled. The gradient is non-zero because it has this dependency on the output of our actor network. So the dependence that gives you a non-zero gradient comes from the fact that we are taking actions with respect to the actor network, which is calculated according to theta super mu, and that gets fed forward through here through the critic network. That's what allows you to take the gradient of the output of the critic network with respect to the variables of the actor network. It's how we get that coupling. And if you read the paper, they actually apply the chain rule, and you get the gradient of the critic network and the gradient of the actor network. This form is actually easier to implement in code. That's why I do it based on the first equation, not the second equation in the paper. It's just easier to do, so why not do it the easy way? Then you want to apply those gradients, which again takes a zip as input. We want to apply, zip up our actor gradient network and the actor dot trainable variables. One other thing I want to point out is that this actor.trainable variables we didn't define. It comes from the fact that we derive our actor network class from the keras.model class. It just comes from the properties of object-oriented programming. Once we have updated the main networks, we want to go ahead and perform the soft update of our target networks. And since this is not the first time we're calling the function, that gets no input, so it will use the default value for tau of 0.005. And that is it, 113 lines for our agent class. Now we're ready to write up the main loop and test it out to see how well it does. Okay, I have an error. It says keyword cannot be an expression. Let's see, rewards, TF convert to tensor. Where have I gone wrong? Right here, it's a period instead of a comma. All right, now we're good. So let's go ahead and start with our imports. We have Jim, we have NumPy, we have our agent, and our plot learning curve. So go to my GitHub, do a git clone, and get those utils. It is just a matplotlib function to plot our learning curve, which is the score versus time, the running average of the previous 100 games over time. It's nothing magical. I don't go over it because it's relatively trivial and doesn't really contribute to your understanding. You can just do a plot of the scores over time to see if it's learning. So we start with making our environment, and we will use the pendulum. And we'll instantiate our agent by getting the observation space from our environment for our input dims, passing in the environment shape, and we will use the default value for our noise and every other parameter because those were good defaults. We'll let it play 250 games. Let's go ahead and define a figure file, pendulum.png. We need to keep track of the best score. That's the lower bound of our reward range. Need to keep track of the history of scores the agent receives, and a load checkpoint. That'll be false. That's if we want to set up our training versus testing. If we're going to load that checkpoint, then we want to set number of steps to 0 while n steps is less than agent.batch size. What we're doing here, okay, so I should explain this. So my understanding, and this could be wrong, if it's wrong, drop a comment down below to correct me. I don't profess to know everything about TensorFlow, but from what I've read from Google, the model loading is set up such that you have to call the learning function before you can load your model. And that's because when you instantiate the agent, you aren't actually loading any values onto the graph, and so it's basically an empty network. There are no values loaded into that network. It doesn't load any values until you try to do something with it. And so we're going to go ahead and fill up the agent's memory with dummy variables, dummy values. They don't really matter. We're just going to go ahead and load it up with dummy values and then call the agent's learn function so we can load our models. And so we can do a random action, doesn't really matter. Get our new state, reward done, and info from our environment. And then remember that. And very important, you want to increment number of steps. Once you've done that, call the learn function and load your models. And set evaluate value 8 to true. And if we're not going to be loading our checkpoint, we'll just say evaluate equals false. I guess we could just use load checkpoint in place of evaluate, or call it evaluate, but whatever. I've used two separate variables, sue me. So for I in range and games, we want to go ahead and reset our environment at the top of every episode. Reset the terminal flag and the score to 0. While the episode is not done, the agent can choose an action based on the observation and the evaluate flag. Get the new state, reward done, and info from the environment. Increment our score and store that transition. If we're not loading a checkpoint, then we want to learn. And the reason I put in that conditional statement is because if you're evaluating the performance of the agent, you probably don't want to disturb its parameters. You want to just go ahead and see how it performs as of the last time you saved it rather than trying to get it to learn a little bit more. Feel free to change that. And very importantly, we want to set the current state of the environment to the new state after the agent took its action. So then we want to, at the end of every episode, we want to append the score and calculate the average to get an idea of whether or not our agent is learning. If the average score is better than the best known score, then set the best score to that average score. And again, if we aren't loading a checkpoint, go ahead and save your models. And at the end of every episode, we want to print some basic debug information. Episode I, score, and at the end of all the episodes, we want to print our, or plot our learning curve. So our x-axis, number of games, okay, that is it for our main loop. Let's go ahead and test it out to make sure I made a sufficient number of typos. But as I said, the first thing we want to do is make dir temp. Okay, I already have that. Make dir temp / DDPG. I didn't have that. And make dir plots. I think that already exists. Okay, now we can go ahead and run the main file and see what I messed up. Okay, so, oh, yeah, of course, our critic network does not get a number of actions. That's something I changed on the fly. So let's fix that here as well. Whoop. And we can go ahead and put this back up here. I think that is right. Let's try it again. Agent has no, oh, it's because it's target actor dot weights, not target actor underscore weights. That is in line 39. So right here, did I do, nope, the target critic was correct. Okay. Has no attribute min size. Okay, oh, it's min action. That's in line 73. Yeah, it's min action and max action. Of course, all right, that's in main, line 41. See, this is why I have the cheat sheet, because even with the cheat sheet, I make a number of typos. So you can imagine what it's like if I were to try to do it on camera. That is in line 41. If not, load checkpoint. There we go. Good grief. Call takes 3 positional arguments, but 4 were given. Oh, that's because I have my parenthesis in the wrong place. Okay. That is in line 92. So the states target action, so the parenthesis goes here. Yeah, that's right. My goodness. Concat missing 1 required positional argument. Oh, because I have the because I have an extra parenthesis. Okay. So this is bad even for me. Line 23. So then we need a second parenthesis there. critic trainable underscore variables. Once again, that is a trainable dot variables. That is in line 98. I thought I looked for that. Oh no, I didn't. Critic dot trainable variables. And I did the same thing here. All right. What, I just fixed that, did I not? Line 100. Didn't I just fix that? No, I did not just fix that. Brilliant. Okay. Actor dot critic dot. Okay. This is what happens when you don't do this for a month. Making YouTube videos is a perishable skill. Okay. Perfect. Now it is actually working. I've gotten through all of those typos and it has started to run. So I'm going to let this go ahead and finish up and we're going to see how it does. All right, so it has finished running and you can see that at the end it kind of tapered off a little bit in performance. If we scroll up, you can see that about halfway through it was achieving record performance with pretty much every single simulation. That isn't entirely atypical with actor-critic type methods. So oftentimes what will happen is the agent will achieve some reasonable performance and then kind of start to taper off because as I said, the actor network is relatively sensitive to changes in its parameters. In this case, it didn't fall off a cliff like I've seen with things like actor-critic or policy gradient methods, but it is still nonetheless sensitive to changes in its weights and is prone to deteriorations of performance late in the number of simulations. If you take a look at the learning curve, you can see pretty clearly that it has an overall upward trend over time. So it is in fact learning. Our technique is working. It's doing its job, but it's not, it's nothing, at least for this environment, it's not the greatest thing since sliced bread. We could do a little bit more tuning to get it even better, but for now, I think this is sufficient to A, demonstrate that it works, and to B, have a solid tutorial on how to implement deep deterministic policy gradients. Once again, shameless plug, if you want to know how to go from paper to code, I show you how in my 2 Udemy courses on deep reinforcement learning, where we go through several papers per course, one on deep Q-learning, one on actor-critic methods, and implement all these algorithms from scratch. I show you how to implement pretty much everything from the papers, minus some superfluous features. Either way, if you made it this far, please leave a like, a subscribe, drop a comment down below, and I'll see you in the next video.